We'll now consider logarithmic functions, which happen to be related to exponential functions, in that logarithmic functions are actually the inverse of exponential functions. So to examine what that looks like, let's just first of all recall what we already know about exponential functions. So in our study of exponential functions, we have recognized that to be an exponential function, we need the dependent variable of y to equal some positive number that is raised to the independent variable of x. And so I did say, right, that a has to be a positive number, but it also can't be 1, so any other positive number that's just not 1, right? So that makes a function exponential. So if we were to then start discussing the inverse of such a function, by our discussion of inverses, we know that inverses of functions are always going to switch the inputs and the outputs in a relationship. So therefore, the equation defined by the independent variable of x equals that same base of a to the dependent variable of y power would be the inverse of that equation. So to help us really explore the territory of this equation right here, we're going to look at this through the lens of a very particular example. That example being right here, the graph of y equals 2 to the x. So that is an exponential function. We're going to graph the inverse of that. So if we were to get the inverse of the equation, the inverse would be that x is equal to 2 to the y. So let's just plug in some numbers for x or in for y and see what we get correspondingly for the other letter. And that'll just give us a nice table of values to see what this graph may possibly look like. So we'll make a column for x right here, and we'll make a column for y, right? So you need to realize from this relationship right here that x is the answer to taking y and raising it to, or taking 2 and raising it to a y power. So, for example, if I were to actually maybe plug in a value for y of 0, right? 2 to the 0 would tell you that x has to be 1. And then if we were to plug in, let's say 1, then 2 to the 1 would equal 2. And if we plugged in 2, we'd get 4 for x. If we plugged in 3 for y, we would get 8 for x. So far we're seeing these ordered pairs on the graph of 8, 3, and 4, 2, 2, 1, and 1, 0 so far, right? Now we could also have negative exponents, of course, and so if we did 2 to the negative 1, that's going to give you 1/2, and then if we did 2 to the negative 2, it's going to give you 1/4 for x. If you plugged in negative 3 for y, you're going to get 1/8. So when x is 1/2, it's about negative 1, and then at 1/4, it's about negative 2, and then at 1/8, it's at negative 3, right? So what is going to end up happening here is as the graph goes down this way, it's actually asymptotically approaching the y-axis. So there is going to be a vertical asymptote right there on the y-axis as the graph is approaching. And then the graph on the right-hand side right there is going to be always continually increasing right there. And so that exactly is what the graph of that inverse is right there. Now, to give you some more understanding of how this is related to the original function, let's also graph the original function, y equals 2 to the x. So if you raised it to the 0th power, it'd be at 1. To the first power is 2, to the second power is 4, to the third power is 8. Here's half and 1/4 and 1/8, right? So this green graph right here would be the graph of y equals 2 to the x, and you'll see that the graphs on the graph right here are inverses because of that property that we know about inverses, and that they always will reflect over this line y equals x whenever we're graphing inverse functions, okay? And that gives us the equation of what we were dealing with right there. So to really help unfold the language of logarithms here and where logarithms are really coming from, let's just kind of go through the process of what we were just doing right here, right? So remember that we started with a function f of x that's equal to 2 to the x, and then what we wanted to do is we wanted to find the inverse of f. And so how we do that is we, of course, replace f of x and x with each other. And so we put it in our first step, we said that x was going to equal 2 to the y. right? And then we were trying to like solve for the y, right? And if we wanted to try to solve for the y and get the y alone, the y would really be like the um, power that we raise to be able to get the number x, right? And then instead of calling that y, we could actually just say that f inverse of x, inverse of x, would be basically the same thing, right? So I can just copy paste exactly what I had right there and just say that it's the power that we raise the 2 to be able to get x. And it just turns out that when we define such a function of the power that we're raising this base to, we actually give it a name. And what we'll call this is we'll say that f inverse of x is equal to log base 2 of x. And so therefore, when we're reading the phrase logarithm, you have to think that logarithm is really just saying it's the power that we raise the base 2 to be able to get x in this particular case. And this is how we really define logarithmic functions. When we define a logarithmic function, we'll say that y equals log base a of x in general for the parent function for logarithmic functions. Really what this means when we say that, if log base a of x is equal to y, then what we know then is that the a will get raised to the y power to equal x. So kind of relating this in a way that will hopefully help you remember this. This number right here is the base, okay? And this also right here is what we call the base whenever we have a power, right? So that base always gets raised to what the logarithm is equal to, and then it's going to equal the x, right? So you can see how a to that y power is then going to equal x. So those are the relationships that we're always going to see exist in logarithms. There's a few different things that we want to make sure are going to hold though. We want to make sure that what we plug into the logarithm, so the value of x, needs to always be positive. So a logarithm is not going to be defined for negative numbers. And you can actually kind of see why this characteristic is going to hold based on what we graphed earlier, because when we graphed this earlier, you can see how the domain of this function actually goes from 0 to infinity. So the only numbers for x that we're able to plug in are numbers that are strictly higher than 0, right? And then in addition to that, we also want to recognize that the base a has to also be a positive number and not be equal to 1. Those restrictions are the same as what we had in exponential functions, because whenever you have an exponential, that base is always positive and not equal to 1. It's just constantly equal to 1, right? Yeah, and so now at the bottom right here, there's just some graphs of exponential functions and its inverse logarithmic functions. There's kind of two different cases, so I'm circling right there. The case where the base is going to be greater than 1, and then the case where the base is smaller than 1, but of course still positive as it needs to be. So you'll see that the gray graphs are the exponentials, and then the red graphs are the logarithmic functions, and see how they're related based on the different types of bases that you might have. These are just very common characteristics that you should be comfortable with and familiar with in terms of the features of the graphs of logarithmic and exponential functions. What we really want to dive into more so importantly, first of all, here is really wrapping our minds around logarithms and just getting some fundamental skills down in regards to logarithms. What you're seeing right here is really meant to be done with no calculator, so definitely as you're working through homework and practicing examples related to logarithms, you'll want to not use a calculator and just use your knowledge about math facts and that sort of thing to be able to determine and figure out all of these sorts of things, right? So in the very first problem right here, we're asked to find the following logarithm, or really just evaluate what log base 3 of 81 is equal to. So as you're thinking about a logarithm, this base right here needs to get raised to the power of whatever this logarithm is going to equal. So 3 to something is going to have to equal 81, therefore. So in this case, the exponent's going to have to be a 4, because 3 times 3 times 3 times 3 is going to equal 81. So that is exactly what the value of this logarithm is. In this case, the logarithm is actually equal to 4. Jumping over to the next example, you have log of a million. The base isn't indicated, but actually whenever it just is log and there's no subscript, you have to assume that the base is actually going to be 10, base 10. And so then you just have to ask yourself, 10 to what power is going to equal 1 million then? It turns out to be 6. So 10 to the 6th is 1 million, so that's going to end up being 6. For the next one right here, when it goes out to the thousandth place and you're thinking 10 to what power is going to equal that, really just count the number of decimal points it goes over. And in this case, it goes 3 decimal points because it goes to the thousandth place. So this is going to be to the negative third power when the decimal point works backwards and goes into decimal points like that. So 10 to the negative 3 is 1/1000. In the next case here, you have a base of 9. So 9 to something has to be able to equal 3. So 3 is not like a power of 9, right? But how they are related, though, is that 3 is the square root of 9. And if you recognize that relationship right there, that should tell you that this is 9 to the 1/2 then, since being raised to the 1/2 power is the same thing as a square root. So this logarithm's value ends up being 1/2. Jumping down to the bottom row of examples right here, you have log base 5 of 1. One thing that you'll start to notice about all logarithms is when you're logging something and there's a 1 right there, you're always going to get the same sort of answer. And you'll kind of see why. So in this case, we want to figure out 5 to what power is going to equal 1. And the only time you can ever really equal 1 when you have a base that's not 1 is if that exponent's going to be 0, right? So it's 5 to the 0 is going to equal 1. So the value of that logarithm is going to be 0. The next one is kind of special because you have the same numbers right here. So we have to ask ourselves 5 to what power is going to equal 5? Well, of course, it just has to be the same number just once. And so this is going to be 5 to the first. So the value of the logarithm is then 1 for that particular one. The next couple actually, require just a little bit more steps of thinking, but they're not crazy. So the next one, you do have a base of 1/8, and you want to raise 1/8 to a certain power to be able to equal 64, right? So like if you did 1/8 squared, you know you'd get 1 over 64, right? But we want to make sure it equals 64. Now you just need to reciprocate it, which means we could just use negative exponents, right? So if you then just made it a negative 2 instead of a positive 2, that would work because we know that 1/8 to the negative 2 is just the same thing as the reciprocal of 8 over 1 raised to the positive 2, which just ends up being 64. So that logarithm then is going to have a value of negative 2. And then in the last one, you do have 16 as your base, and 16 needs to be raised to something to be able to equal 2 square root 2. Okay? So it needs to get smaller than 16, right? So that means we're going to have to use some exponent that is going to be probably fractional or negative or something in nature, right? So you probably want to try to establish some sort of relationship between the square root of 2 and 16, right? So like we do know that 16, if it was raised to the half, is going to equal 4, right? But then if you were to take both sides of this and raise it to the half, we would know that we would get 2, because that's the square root of 4. And then 16 to the 1/2 to the 1/2 is 16 to the 1/4. And if you raise 2 to the 1/2, that would give you the square root of 2, which would tell you then that 16 to the 1/4 to the 1/2, which is 16 to the 1/8, is actually the square root of 2, right? So to actually be able to get 2 times square root 2, this is really the same thing as square root 2 times square root 2 to give you the 2, and then plus another square root 2, right? So ultimately, this is 3 square root 2's that are all multiplied with one another. And so since the square root of 2 is the same thing as 16 to the 1/8, then this right here is actually the same thing as 16 to the 3/8 then. And that would, of course, be the value of the logarithm. So in this case right here, it has to be 3/8. So just a couple of special things you wanted to notice. from a couple of examples that we just saw right there is that whenever we have a log of any base a that's positive and not equal to 1, and you are taking a log of 1, that's always going to equal 0. So that's one important property you should be able to recognize. And then also, whenever you do log base a of a, where you have those same numbers right there, that's just going to equal 1, because a to the first is going to equal that a, as you see there. So just a couple of special things that you want to definitely recognize. Yeah, so proceeding forward here, you'll see right here that we are asked to write each exponential equation as a logarithmic equation. So you'll have to recognize and understand that whenever we write something as an exponential equation, so let's say that you do a to the b and it equals c, that's always equivalent to taking a log, and it's going to be of base a, because that was the base of your exponential expression, and then all of c is going to equal the exponent of b. So those things are all equivalent. And so we're asked right here to take all of these equations right here, and these are all in an exponential form, and we just want to write the equations in their completely equivalent logarithmic forms. Okay, so in the very first example right here, we're seeing that 5 to the x is equal to 125. So if we write this equation as a log, we want to use the same base as our base of the logarithm, log base 5, and it should be of the answer, and that equals the exponents. And this gives us that same equation in logarithmic form. And you can always check, like you should know that 5 needs to be raised to the answer power to be able to equal 125, right? And that's exactly the same equation that we started with. So we know that that's going to be able to work. In the next case, you can see that 10 to the negative 1/2 is indeed equal to the square root of 10 over 10. So in this case, your base is 10, so we'd want to use log base 10. But remember that if it's base 10, we could just write only log, and so that's generally preferable. What you'll see more often is just log when it's base 10. So that's all we need to write. So if we said log of the square root of 10 over 10, it's going to equal the exponent of negative 1/2. Yeah, and so for the rest of these here, you'll have that the log with a base of 3/2 for this one of 8 over 27 is going to be able to equal negative 3. And then finally, for the last one, your base is e. So a log with a base of e of the number z should equal the exponent of 1/5. So all of those now get into logarithmic form from their exponential forms. And then we also want to make sure that we're comfortable going backwards. So here we're asked to write each logarithmic equation. So these three examples are given with logs, and we just want to convert it into its exponential form. So let's just very simply take the base and raise it to what that answer is, power, and it should equal right there, the 36. And we know, of course, that's true, right? 6 squared is 36. So in this case right here, your base is 10. So that 10 would have to be raised to the 0 power, and that's going to equal 1. Of course, that's true, because anything to the 0 power is equal to 1. And then finally, your base right here is 1 over x. So it's going to have to be raised to the m. Now, when you do that, you can't just put the m right there, because then it looks like it's only the 1 being raised. So you want to make sure you put in parentheses 1 over x, so that we know that that whole fraction is being raised to the m power. And then the answer of that is going to equal the square root of t. They're in exponential form. All right, so now we want to start getting into some of the funkier sorts of logarithmic values. And so to kind of exemplify that a little bit right here, let's think about log of 43 for a little bit right here. So really what that means is this means log base 10 of 43, which would be equivalent to saying that 10 to some power is going to have to equal 43. Right? Well, that's a little perplexing because like 43 is not like a perfect square or perfect cube or anything of 10. 10's not going to go into that very nicely, right? So like what we definitely do know is we do know that 10 to the first is equal to 10, right? And then we also know that 10 squared is equal to 100. So 10 to something equals 43. Well, 43 is between 10 and 100. We might intuitively think that maybe this exponent right here has to be somewhere between 1 and 2. And it turns out that we're right. So like the only way that we could really do this nicely is using a calculator really to get an approximation at least of what this would be equal to. So on your calculators, you should have just a log button. And so your calculators are going to be set to already be in base 10. So if you just use that log button, it should evaluate. So literally just type log and then put 43 into a calculator. And when you do log of 43, it'll tell you it's going to be about 1.6335. I'm rounding to about 4 decimal places to give somewhat a little bit more accuracy to the values of the logarithms right here. So with all these other examples right here, you're just asked to evaluate using a calculator, right? So it's just typing them all in. So I'll go through them and you can do it on your own in your calculator just to check to make sure that you're getting the same values that I am here too and such. Again, going to 4 decimal places. We're going to expect to definitely see a negative exponent for this log of 0.00003107 for sure. Yeah, it turns out to be about negative 4.5077 if we round that there. And the last one, you'll see that we have a negative number inside of a log. You'll remember the domain of logarithms is any positive number. So anything above 0 can't plug in 0. So this one's going to kind of like come up with an error or something on your calculator. So my calculator, it says there's an error in the domain. So like this value right here just doesn't exist because -1 is not in the domain of like a logarithm. So yeah, it just doesn't have a value. All right, so a natural logarithm is still a logarithm, but what makes a natural logarithm special right here is that when you have a logarithm of base e, okay, then we call this the natural logarithm. And what we'll write is we'll write ln of x to be equivalent to log base e of x. So this ln right here is just a symbol that we'll use whenever we're doing a natural logarithm and we're dealing with things of base e. So you'll see what that looks like with examples right here. All 6 of these examples use this ln, so just a natural logarithm, meaning that we're really dealing with base 3, right? So in the very first example, when we're doing natural log of this, you're really thinking, okay, if I had e and I raised it to whatever this answer is, power, is going to equal 243,628. Okay, so on your calculators, there should be an ln button for you to be able to approximate logarithms. So if you just use that ln button and then type in 243,628, it'll tell you the value of this is about 12.4034 when you round it to the nearest 4 decimal places. And really what this means is that e to the 12.403 is going to equal 243,628. We'll evaluate that. Right. Yeah, and then punching in some of these other ones up in the top row right here, we're going to get, this one's going to be about negative 10.3793. And then this one also is plugging in a -1, which is not going to be in the domain of a natural log because a natural log is still a logarithm. It just has a base of e only. So this value right here, again, is not going to exist. You'll get the same error showing up on your calculator, whatever you had from before. The bottom row, so I should maybe note that these were meant to be done with calculator. And then these examples right here are really meant to be done without calculator so that you start to become really comfortable with understanding the meaning of logarithms. And so in this example right here, you have base e and thinking e to what power is going to equal e. And so it just turns out, right, that natural log of e is just going to equal 1. Okay, and that should be a commonly known fact that you already know. I do want to add an extra example in here. So let's say that we had natural log of e to the 11th. Okay, really what you're thinking then is you're thinking e to what power is going to equal e to the 11th. Well, of course, the only thing that's going to make that true is 11, right? So that's going to equal 11 as a little extra example there. If you're doing natural log of 1, we talked about a property of logarithms earlier, and that that's just going to equal 0 whenever you're natural logging 1, right? And the reason why that is e to something has to equal 1, and the only way that can hold true is if that exponent is going to be 0. So our answer there is going to be 0. And then finally, we're natural logging 1 over e to the 5th. Now, we do know that 1 over e to the 5th is the same thing as e to the negative 5th. And so if we're thinking e to what has to equal e to the negative 5th, well, of course, it has to equal negative 5, right? So that would be the value there. So hopefully all those examples there in the bottom, you'll be able to do just fine without having to use a calculator at all. All right, so there are going to be many times when we are trying to evaluate a logarithm where the log button in your calculator, which is base 10, and then the natural log button on your calculator, which is in base E, aren't going to have all the tools that we need because we oftentimes want to find values of logarithms that correspond to bases like base 8 or base 6 or base half or whatever it may be. So the change to base formula really enables us to evaluate logarithms where the bases go outside of just a base 10 or a base E. So what the change of base formula says is that if you do a log of base B of, let's say, I don't know, like Z, how about? Then it's really just the same thing as the log base anything of Z over log base of that same anything of B. So as examples right here, we're going to try to evaluate this log right here using a common logarithm. And really what that means is just to do a log, meaning log base 10. And then we're going to do the same thing, but then also use natural logarithms, meaning use natural log. So log base 8 of 24 is just the same thing as doing log of 24 over log of 8, where now both the logs on top and bottom are both in base 10. When you put this in a calculator and you just type log of 24 and then you divide it by log of base 8, you're going to get approximately 1.5283 to the nearest 4/10. But it doesn't doesn't matter if this was base 10, it can be any bases. So if you use base E and just did natural log of 24 over the natural log of 8, that's buttons that you can push in your calculator. And if you did natural log of 24 and divided by natural log of 8, it turns out that that's going to be 1.5283 rounded to the nearest 4 decimal places. And of course, you get the same thing, right? So that's done using both common logarithms and natural logarithms. I do want you to understand that if you were to do log of the 24 over the log of the 8, right, you can literally choose any base. So if you're going to do like base 2/3 right here, then you can make this base 2/3, and when you do log base 2/3 of 24 divided by log base 2/3 of 8, it's still going to give you the same 1.5283 using this change of base formula. So it's a really useful tool to be able to evaluate logarithms when we know that we're dealing with bases that are different than just 10 and different than just base E. Okay? All right. So we're going to look at graphing various logarithmic functions right here, mostly just kind of building some intuition by making a table of values to understand why the points are on the graph and where they are. And then just some very basic transformations of logarithmic functions here as well. So we're here to graph log base 5 of x, which of course means we're thinking that 5 needs to be raised to the f of x, or to the y power, to be able to equal x. So you should be able to construct a table of values for this to kind of figure this out. It's probably easier to just plug in y values into this and do 5 to that y value and then figure out what the x is based on that. So if we plugged in, say, 0 into the power, 5 to the 0 is going to equal 1. If you plugged in 1, you would get 5. You plugged in 2, you get 25. 3, you get 125 when it's cubed, right? And then, of course, when you plugged in negative exponents, you just get the reciprocals of all of those things, 1 over 5, 1 over 25, 1 over 125, etc. So if we plot as many of these points that we can fit on here, we can fit 5, 1, and we can fit 1, 0. 1/5 goes down to -1, so it's really just going to kind of go like this, and we know it has an asymptote right there in the y-axis, and it goes like that. So that gives us the nice, beautiful graph of log base 5 of x. Okay, so if we contrast that with, say, like a little different base, this right here would be natural log of x, which we know is the same thing as log base e of x, right? Or it's like 2.718. So we have a little bit of a smaller base than what we just had before when we had base 5, right? So again, we can make a table of values to figure out some key points that are going to be on this. So we know that graphing natural log of x is like the same thing as taking e and raising it to the g of x or the y power and equals x. So if we plugged in 0 into the exponent, then e to the 0 is 1. If you plugged in 1, you'd get e, which remember is like 2.718. If you plugged in a 2, you'd get e squared. And e squared is like 7 point something. It's like 7.390 or so, right? So yeah, we could like go to 7.39 and go up to 2, so it'd be right about there. 2.718 for x goes up to 1, so it'd be like right about there. And then we do have the 0.10 on here as well. And then if you plugged in some negative exponents, you'd get 1 over e. 1 over e would be about 0.367. So at that for x, it'd be at about -1. So like that. And that's good enough. You know that it's going to trend downwards like that and trend upwards like that. And that gives us the graph of the natural log function. So using this graph here of g in the next three examples, we're just going to do some transformations of this particular function, just some shifting and reflecting and that sort of stuff. So if we were to take that natural log function that we just graphed, and we were to do natural log of x plus 4, it really just means that we're going to move the graph to the left 4 because we're plugging in x plus 4 instead of x, things that we already know about transformations. So if you recall, we had this point right here, which was e1 on our graph initially, and then e squared was like 7.4 or something. So this was the point e squared 1, and then right here was the point e to the 0, which is 1, 0, right? And then we had like a point down here. So this was basically what our graph ended up looking like, right? So if we were to take this graph and turn it into the transform graph, what we'd want to do is just take that graph and then just slide it exactly 4 to the right. So I think the easiest way to kind of tell that is if we originally had an x-intercept right there, you can see now that the new x-intercept has moved 4 to the left to now, yeah, -3. And so that would be the graph that would be transformed by translating left 4 units. This graph right here would also take the same natural log function, I guess. And then what's going to happen is it's going to get compressed by 1/2. And then there's also this vertical reflection that's going to happen, or a reflection in the x-axis because it's negative. And you can see that that 3 right there is also going to do a vertical translation up by 3 units. So let's first of all just do this piece by piece, and let's graph the parent function y equals the natural log of x. So we'll have the point e1, e squared 2, e to the 0, 1, this point approximately there. Okay, so we get this. This is y equals natural log x. So if we were to maybe reflect this first of all. So first I'm going to do y equals negative natural log of x. That's going to flip the graph upside down. So we end up getting this point here, 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 right there. So it's going to look like this once it goes upside down, right? And then we also know that second of all, it's getting compressed. So y equals -1/2 of natural log of x is going to compress the graph by a factor of half. So all the y values are going to be cut in half, basically. So like right here where it went down 2, it's only going to go down 1 right there, and this is only going to go about half as far. It's still going to have the same x-intercept. And then at that point right there where it went 1 high, it's only going to go like half as high. So it's just going to be a much kind of flatter sort of looking graph because of the compression that was happening here. And then finally, the third thing that needs to happen right here is that we need to then take that and shift it up by 3 because of the adding of 3 happening there. So that blue graph is really just going to move up 3 points for all of these different points and kind of will look something like this then, once everything gets shifted up by 3 units. So that green graph then would give you the final result for the graph of that logarithmic function. And then finally, with the last example right here, something a little funkier, but it's pretty easy to understand once I explain it to you right here, is there's an absolute value around this. And we'll talk about what the effect that has. If we first of all just think about having the natural log of x minus 1 equals y only, so that would really just be taking the natural log function and shifting it to the right one, of course. And so we'll deal with that aspect. So let's go ahead and graph the natural log function first by going to e1 and e squared 2, 1, 0, and 1 over e negative, like that. So that would be the y equals natural log of x. And then if we were to take that graph and shift it to the right one, we would end up getting this blue graph right here, which is y equals the natural log of x minus 1. Okay, so what we want to do is we want to absolute value this graph here now. And what we know is that an absolute value is always going to make everything positive, right? And so that's really going to affect the y values only. And so wherever we have negative y values, they should become positive. So this part of the graph right here that is negative is actually going to get reflected upwards. So this part right here, when it gets reflected upwards, is going to kind of go like this and have that asymptote along x equals 1, because remember we shifted everything to the right. And so really this along with this right here is going to be the graph of our function. So I'm going to erase some of this other scratch work so you can really visualize exactly what I'm trying to show right here. So it's those two purple pieces put together that gives you that graph. So that absolute value really just made whatever is negative for y ultimately become positive. Okay. And then one last final example for logarithms right here. I'm just going to look at an application of being able to use logarithmic functions. So it turns out that in chemistry, the pH of a substance is defined as the pH, which is equal to negative of log base 10 of H plus, where that H plus is defined as the hydrogen ion concentration measured in moles per liter. So in part A, we are asked to find the pH of mouthwash, which happens to have a hydrogen ion concentration of 1.6 times 10 to the negative fourth, right? So if we're trying to find the pH, we're trying to figure out what this like y variable ultimately is, right? And we're given the hydrogen ion concentration. So if we were able to take this negative log function and then just plug in 1.6 times 10 to the negative fourth, that should be able to give you then what the pH value is, right? And so you do have the tools in your calculator to be able to evaluate that. So if you took negative log and then just typed in 1.6, multiplied that with 10 to the negative fourth, and evaluated that, it would give you something that's about 3.795 in terms of a pH level for mouthwash. So something that's quite a bit more acidic, since things are a little bit more neutral, like tap water at 7, right? So much more acidic when you have mouthwash, of course. Now it turns out that orange juice is a little bit even more acidic. It's got a pH of 3.2. So given that, we want to determine its hydrogen ion concentration. So now we actually know the pH, so we could plug in 3.2 for the pH, and then set that equal to negative of the log of whatever this hydrogen ion concentration is, and then solve to determine this. Now, probably the easiest and best way to be able to solve this is to graphically be able to solve this. So you should be able to graph the negative log of x function, and then also be able to graph y equals 3.2. And if you can figure out where those graphs are going to cross at, then that should give you the solution or approximate solution for what the hydrogen ion concentration would end up being. So I'll just pull this up on Desmos where we can find the intersection of these couple of graphs then. So we'll graph y equals negative log of x. So I need to go to my functions and find the log function. Yeah, log base 10, and we'll just say it's of x. And then we also want y equals 3.2. Yeah, and so you'll be able to see then that where those graphs are intersecting at is at the point 0.001 and 3.2. So that would tell you that that x value has to be 0.001. You know that that is like 10 to the negative third, right? So therefore, um, this right here, the h plus or the x value has to be about 0.001, or in other words, really just needs to be about 10 to the negative third, or we can write that as 1 times 10 to the negative third in more scientific notation there as well.